Okay, continuing on to advanced measurement error. So basically, this comes out of calculated quantities. So suppose I have to add two quantities together that I measure to get a quantity I'm interested in. So say x equals a plus b or a minus b. So for example, if my head is 160 centimeters plus or minus a centimeter, and my hat is 2 centimeters plus or minus a half centimeter, if I put my hat on my head, what's the uncertainty in the height of the hat? I have to include both of the uncertainties, the uncertainty in the measurement of me and the uncertainty in the measurement of the hat. What about multiplication or division? What about if I'm multiplying two things together and each of those things has some uncertainty to it? How does that propagate into the error that I might get in the answer? So for example, suppose my classroom is 12 meters by 4 meters, and the length has an uncertainty of a half meter, and the width has an uncertainty of 0.4 meters. What's the uncertainty in the area that I get by calculating? So as a very rough rule, you guys have probably learned with sig figs, is you just keep the smaller number of decimal places when you're adding or subtracting. So for example, if you're adding, say, 1.21 to 2.4, then you just get together and you go 3.6, and you say, that's trash anyway, because this isn't even as precise as that, so I'll just keep the lesser amount of precision. With error analysis, you're basically doing the same thing. It's a very rough rule of thumb. You add the absolute uncertainties. So that's a centimeter in my height, that's a half centimeter in the hat height. So if I just add those together in this very rough way, I would get an uncertainty of 1.5 centimeters. That's what you're doing in sig figs. You're adding things together with a very rough rule of thumb. Multiplication division. So maybe you recall that when you're multiplying or dividing two numbers by each other, you just keep whichever number has got a smaller amount of sig figs. So for example, if I were multiplying the number 20 times the number 43, you'd have 860. But since this number only really has one sig fig, that should be rounded to 900. So again, this is not like mathematically true, because it is really 860 if these were exact numbers with the complete precision. But in a science sense, if these numbers were measurements, then 20 would be rounded to the nearest 10. So you would round this to 900 because this is the smaller number of sig figs. With error analysis, the rough rule that you would use is the same thing, in that you would add the relative uncertainties. That's why you're keeping the smaller number of sig figs, because it has this effect of adding the relative uncertainties. So to calculate my relative uncertainties, so the length, the relative uncertainty is 0.5 over 12, which is a 4.2% uncertainty. The width, 0.4 out of 4, which is a 10% relative uncertainty. So if I get 10% uncertainty in one dimension and 4% uncertainty in the other, then the total uncertainty in the area, which I've gotten by multiplying them together, is 14.2%. So really what I would get is that the area is 12 times 4, 48 square meters, but my uncertainty is 14% of that, so it would be plus or minus about 7 square meters. This is very different than what would happen if you just multiply the uncertainties together, right? 0.5 times 0.4, that would just give you 0.12. This is a much bigger number. If you want proof that it really should be this much bigger number, think about what happened if you dramatically undermeasured both. 11.5 times 3.6. Think about what happened if you dramatically overmeasured both. 12.5 times 4.4. You would wind up with a number about twice as big as that in terms of the difference that you get. So if you actually run the numbers through there, you do wind up with a bigger amount of error when you're multiplying things together. But this is not the full story. Right, this idea of the measurement is number plus or minus uncertainty kind of plays around with this idea that, okay, there's an average, and then plus or minus some distance from the average, and you're just going to hit anywhere on that line with equal probability, and you're never going to hit outside of that line. Well, keep in mind that if you guys have done statistics, then what you use for uncertainty on any measurement that you get that has high precision, you're using the standard deviation as your uncertainty. So really, you're not getting this picture, you're getting this picture. So how much variation you might get in the measurement is really a statistical probabilistic statement. We're not going to include the crazy outlier measurements that happen very rarely. We're going to say, okay, maybe around 2/3 of the time, how often am I some distance away from that average in my measurement? And on top of that, I'm more likely to be close to the average than I am to be further away from together. So really, I've got to take a fuller treatment on this to get a more complete picture. So it actually is extremely unlikely that you will severely overmeasure both variables at once or undermeasure both variables at once. Because what's happening is you're making a measurement of one variable. So you might get a measurement here, 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 here. But more often than not, you're going to wind up in the middle. And then the other variable that you're measuring, you might overmeasure it, undermeasure it. But all in all, most of the time you're going to land near the middle. So really, if I want kind of an error of something I got by multiplying these two things together or adding them together, whatever, most likely what's happening is it's going to be some kind of a mix. So really, I need to make a new standard deviation out of the standard deviations of the underlying things that I've measured. So really what I have to do is I have to add these like so. So if this is the standard deviation of one measurement, say x, and this is the standard deviation of some other measurement, y, then really a more fair treatment than just assuming that I've got the same standard deviation of both, I'm going to severely undermeasure both or severely overmeasure both, is this right here. So really what I should do is figure that the total standard deviation squared will be the standard deviation squared in x plus the standard deviation squared in y. So your old friend the Pythagorean theorem is invoked here. Because the idea is that any errors that I get in one measurement are unrelated to errors in the other measurement, operating on the assumption that my variables are uncorrelated. So when you do the full treatment, what you wind up with here is that instead of my height having an uncertainty of 1.5 centimeters, which we got just by adding the 1 to the half centimeter, if you do this in quadrature, meaning the Pythagorean theorem, you'll have 1 centimeter squared plus 0.5 centimeters squared and then square root it. You're actually going to get a smaller standard deviation, only about 1.1 centimeter. Gets even more dramatic when you get into multiplication. So we originally said that the uncertainty in the area should wind up being 14%, because you just add together the relative uncertainties, and that gave you an uncertainty in the area of 6.8. If you add them together in quadrature, you actually get a tighter result. You get that the uncertainty is going to be 4.3%. So that's this 0.04 squared plus 0.1 squared square rooted. Only 4.3%, so the uncertainty in your area is actually only 2.1 instead of 6.8. Still bigger than what you would have guessed just by multiplying the uncertainties together, but it's a lot smaller than it would have been with this rough treatment we tried at first. So this rough treatment of just adding together the uncertainties, or just adding them together the relative uncertainties, that's going to be an overestimate for how bad it might be. If you add them together in quadrature using the Pythagorean theorem, you will get a tighter result, better than the worst case scenario. And one last note I'll leave, you can always add more variables in. So standard deviation squared plus standard deviation squared plus standard deviation squared. And then this is just the general formula. I talked about adding and subtracting to calculate a new thing, or multiplying and dividing to calculate a new thing. But of course, there's an infinite number of functions out there that tell you how to calculate a new thing. So you would be doing partial derivatives to figure out what those are. It just so happens that when you are adding two things together, you get a partial derivative of one, and when you multiply things together, you get a partial derivative of whatever the other variable is, basically. So this would be the full treatment if you're dealing with anything else besides addition or subtraction, or just multiplication, division, or you've got more than two variables involved. And even this equation, which you'll find on Wikipedia, is a simplification under which we're assuming that all the variables are uncorrelated to each other. If the variables are correlated to each other, then it gets even uglier than this. But this is your full treatment, which is going to be good for basically your purposes. And if you add the standard deviations together in quadrature, that'll give you your full treatment. But of course, if you just want to do that thing with the sig figs, it works. But this is why the sig figs things work. The sig figs are a rough rule of thumb that actually give you the worst case scenario. In reality, if you're a little bit more rigorous about it, you actually have a little bit more strength in your conclusions than you think you do, and your uncertainty is actually smaller than the worst case scenario.